Okay, let's dive in. We're looking today at something pretty fascinating in AI, specifically large language models, LLMs,
hmm
and how they generate those sequences of intermediate steps, the things people call chains of thought.
Right, SUAT. And it's become really common, almost second nature, to see those steps as the model actually thinking, like it's showing its work.
Yeah, exactly. You hear people say the models are reasoning or backtracking, even having metacognition.
For sure. Like that DeepSeek R1 paper,
Yeah.
they talked about seeing an aha token.
Oh, yeah, I remember that. Interpreted as like a sudden insight inside the model.
Exactly. Which sounds cool, but the paper we're digging into today basically says, hold on a minute.
Okay.
It asks, do those intermediate tokens really need to mean something? Do they have to be a faithful step-by-step process to actually work?
Or something else going on. Interesting.
Yeah. Could their usefulness be totally separate from whether they represent thoughts? That's the core question here.
All right, so our mission for this deep dive is to unpack that paper, see how they tested this, and what they found. Because it definitely pushes against that intuitive idea.
It really does.
So first off, why is it so tempting to see these things as thoughts? You mentioned the aha moment.
Well, it's correlation mostly. You see, these models solve really hard problems, right?
Yeah.
And they output this long sequence that looks like reasoning steps.
Okay.
So the natural jump is the steps cause the solution because they are the reasoning. And the language we use, thinking, aha, reinforces that. We kind of anthropomorphize it.
We fit it into how we think.
Exactly. And the paper we're looking at calls that kind of interpretation, like the aha token, unwarranted. A strong word.
Okay, strong word. So the results are impressive, the steps are there, assumption follows. But why is it so hard to just check, to verify if the steps from a big model like GPT-4 or Claude are actually, correct or meaningful?
Yeah, good question. It really boils down to opacity and scale. These frontier models are just enormous black boxes. The reasoning traces they output, they can be super long, kind of rambling, written in natural language, which is inherently ambiguous.
So trying to formally check them against some ground truth algorithm is...
Almost impossible. Plus, you often don't even know the exact training data or the fine-tuning process. It's proprietary or just way too complex.
You don't have a clean reference for what correct steps would even look like for that specific model on that specific task.
Precisely. There's no clear blueprint to compare against.
Got it. So massive opaque systems make verification tough. How did this paper get around that? How do they actually test the meaningfulness of the steps?
This is where their method gets really clever, I think. They use what they call the model organism paradigm.
A model organism, like in biology.
Exactly like that. Instead of trying to understand, say, genetics by only studying complex humans, biologists study simpler things, fruit flies. C. elegans worms.
Okay.
So here, instead of the giant opaque LLM, they use smaller, fully controlled models. Open, replicable, trained from scratch, just for these experiments.
Ah, okay. A controlled environment to really isolate the variable they cared about, the intermediate steps. What was the task they used for this model organism?
They chose shortest path planning, specifically in randomly generated 30 by 30 mazes.
Why mazes?
It's a great choice. It's a classic computer science problem pathfinding. Crucially, it has well-defined, formally verifiable algorithmic solutions.
Like a search?
Exactly. They used a search. And this task also builds on some previous work where people had trained transformers to mimic algorithmic traces.
Okay, and the model wasn't huge then?
No, it was a modified Qwen 2.5 model, the 0.5b version. So around 380 million parameters. Manageable. And importantly, they trained it from scratch themselves.
Full control over training data and the model. That makes sense for this kind of rigorous test.
Absolutely essential.
So they have the controlled model, the formal task. How did they get the correct reasoning trace? The ground truth for A in the maze?
They used the A algorithm itself, ran it on each maze to find the guaranteed shortest path. A works by evaluating nodes using that Fn, Gn plus Agn cost function.
Right, costs so far plus estimated cost to go. Using Manhattan distance here, probably.
Yep, consistent Manhattan heuristic, standard for grid mazes. He keeps track of nodes to visit, nodes visited.
But that gives you the path. How did they get the trace, the step-by-step intermediate tokens the model was supposed to learn?
So they didn't just record the final path. They generated what they called linearized execution traces directly from the A algorithm's process.
Ah, like logging the algorithm's internal actions.
Exactly. The trace would be a sequence of tokens representing things like create node, XY, with cost G, heuristic H, or close node XY. It captures the step-by-step operation of A.
Okay, that's neat. But here's the really innovative part you mentioned, the academic contribution, the formal A trace validator. What's that?
Yes, this validator is absolutely key to the whole study. It's not a human reading the output. It's a piece of software, a program they built.
Okay.
And this program takes the sequence of tokens the model generated its supposed reasoning trace and formally checks if that sequence actually follows the strict logical rules of the A algorithm.
So it's like an automated rule checker for the model's homework. Not just, is the final answer right, but did you follow the A rules step by step in your working?
Precisely that. It can spot specific errors defined by A's logic. Like, did the model try to expand a node that wasn't actually the one with the lowest cost? Did it pick a neighbor that isn't valid? Did it claim to reach the goal when it hadn't?
Wow, okay.
And this allows them to make a critical distinction, something you just can't easily do with big LLMs on messy real-world text. They can separate plan validity.
Is the final path through the maze correct?
Right, from trace validity.
Do the intermediate steps the model wrote down actually formally semantically match the A algorithm's process?
Exactly. This objective programmatic measure of trace correctness is the core innovation enabling their experiments.
Okay, killer setup. Controlled model, formal task, a ground truth trace, and this validator to check the model's generated trace. So what happened when they trained models on correct, valid A traces? What was finding number one?
Well, the first finding was already a bit of a crack in the CoTs thinking narrative. Even when models were trained perfectly on correct A traces, there was only a loose correlation between the formal validity of the intermediate trace the model generated and the validity of its final solution path.
Wait, loose correlation meaning?
Meaning a model could generate a trace full of errors, according to the A validator, but still spit out the correct final path through the maze. Or the other way around, it could generate a trace that looked pretty good, mostly followed the A rules according to the validator, but then the final path it proposed was wrong.
So getting the steps right didn't guarantee the right answer, and getting the steps wrong didn't guarantee the wrong answer.
Exactly. That was the first clue. The idea that the intermediate steps must be semantically correct to guide the model to the right solution. It didn't hold up perfectly, even here.
Okay, that's already interesting. But then comes the experiment that sounds really wild, the swap data set. What on earth did they do there?
Yeah, this is the real mind bender. It was designed specifically to hit that question of semantic meaning head on.
Okay.
They took their data set mazes paired with their correct A traces, and then they randomly shuffled the traces.
Shuffled, you mean?
Well,
Maze A in the training data might be paired with the correct A trace that was originally generated from Maze Q.
that's exactly right.
Right.
Maze A gets Maze Q's trace. Maze B gets Maze X's trace randomly assigned.
Whoa, okay, hang on. So the trace that the model sees during training looks like an A trace, structurally. It has the right kinds of tokens, the create, close, coordinates, costs.
Yes, it maintains the form of an A trace. It has the right syntax, the right vocabulary for the domain.
But it has absolutely zero semantic connection to the actual maze problem it's paired with. The steps in the trace are totally irrelevant, completely wrong for that maze.
Precisely. If you ran the validator on Maze A using the swap to trace from Maze Q, the trace validity would be 0%. It's structurally plausible noise, semantically speaking.
Okay, my brain hurts slightly. Surely, draining a model on this, garbage data, essentially, must lead to terrible performance. The model would be learning complete nonsense relative to the task.
That's what intuition screams, right? But this is the absolute killer finding of the paper.
Tell me.
The model trained on these swapped, semantically meaningless, irrelevant traces performed comparably to, and in some challenging cases, significantly better than, the model trained on the original correct A traces.
Better? How? Why? That makes no sense.
I know, it's deeply counterintuitive. The difference was especially noticeable on harder out-of-distribution mazes, things like Drunkard's Walk mazes, which have loops and look different from the training mazes.
And the SWOT trace model did better on those.
Significantly better. They gave an example where, on one type of Drunkard maze, the SWAF model got 26% plan validity finding the right path 26% of the time.
Okay.
The model trained on the correct traces, only 2.6% on that same challenging task.
Wow. So, generating a formally incorrect trace, one with 0% semantic validity for the problem at hand, led to better generalization and problem solving on tough, unseen problems.
That's what their results showed. It directly led to their strong statement, which you quoted earlier. trace correctness can actually be an albatross for the model's performance.
An albatross, wow.
Sure.
So trying to force semantic correctness can actually weigh the model down, hinder its ability to find the solution, especially on new problem types.
Seems like it, in this controlled setup.
Yeah.
And they didn't just stop at mazes. They did similar experiments with Sokoban puzzles and other complex planning tasks.
And found the same thing.
Pretty much. Training on correct Sokoban, step-by-step solutions didn't give a major boost over training on swapped incorrect traces, so it wasn't just a quirk of pathfinding.
Okay, this totally flips the script on CoTs. If the steps don't need to be semantically meaningful or correct, why do they help at all? Because CoT does generally improve performance, right?
It does. That's well established. So if it's not the semantic content, what is it? The authors offer a hypothesis. They suggest that generating these intermediate tokens acts as a form of prompt augmentation.
Prompt augmentation,
Meaning the act of generating that sequence of tokens, regardless of its semantic content, changes the model's internal state or effective input in a way that helps it perform the final task better.
So it's not that the model is using the steps it writes like a human would, following them logically. It's more that the process of generating that specific pattern of tokens somehow primes or guides the model internally.
That seems to be the idea. The sequence generation itself is a learned procedure that puts the model into a better configuration to solve the actual problem, even if the sequence content is meaningless to us or even formally wrong.
And crucially, this augmentation doesn't need to be human-readable or interpretable.
Exactly. They point to parallels in adversarial prompting research, where weird, nonsensical strings of characters can somehow jailbreak an LLM or steer its behavior in unexpected ways.
Right, gibberish can still act like a powerful instruction.
So maybe these reasoning traces are like complex, learned internal prompts. They work, but not because they represent thought as we understand it.
That's a really different way to think about it. So what are the big implications here, the main takeaways from this research?
Well, the biggest one is probably a huge dose of caution about anthropomorphizing these intermediate outputs. Seeing them as thoughts or faithful reasoning seems shaky based on this.
But that aha token maybe wasn't an aha moment in any cognitive sense.
Probably not in current models, yeah. The effectiveness just doesn't seem tied to semantic faithfulness, whether human-like or algorithmic.
Okay. And for the folks actually building and training these models, what are the practical implications?
It suggests that spending a lot of resources trying to force models to generate perfect, human-readable, semantically correct traces might be unnecessary.
Or even counterproductive based on the albatross finding.
Potentially, yeah. Maybe research effort is better spent understanding what features of these generated sequences do help the structure, the length of vocabulary, rather than focusing solely on their step-by-step semantic accuracy.
And what about training data? Does this mean we don't need perfect reasoning examples?
It certainly questions the necessity of perfectly curated, step-by-step valid traces. Maybe simpler methods, generating structured sequences that aren't necessarily correct but have the right statistical properties, could be explored, generating useful noise, perhaps.
Useful noise. Okay.
So, just to sum up that core finding again, intermediate tokens, like CoTs, they do help performance. But this research strongly suggests it's not because they contain meaningful thoughts or accurate reasoning steps.
It's more about their role as a learned kind of prompt augmentation.
Exactly. They modify the process in a beneficial way, but not necessarily through their literal meaning.
Right. And that leaves us with a pretty provocative thought, doesn't it? If models learn to generate patterns, maybe even patterns we see as incorrect or nonsensical noise to solve problems effectively, what does that really mean for interpretability? Are we potentially trading transparency for performance? If the most effective internal prompts are things that don't make sense to us, can we ever truly understand how these advanced models arrive at their answers, especially on really complex tasks?
Yeah.
It definitely gives you something to chew on next time you see one of those long CoTs outputs.